guztioi, mila esker guztioi. So thanks a lot for coming, in particular to the undergrads, because they are between the first call of exams and the rest. So it's the holidays. And so thanks a lot for, especially to the undergrads. So today we have EHU's Quantum Center Colloquium, which is going to be given by Alexandre Blais. I have to actually read the explicit name, which is towards quantum computing with superconducting circuits, which is actually the topic that Professor Blais has been involved in for quite some time. His PhD thesis is called Algorithms and Architectures for Superconducting Quantum Computers, with Tremblay and Lasselle. Of course, in his jury, in his panel, you had Michel de Boré, amongst other people. And then he went to Yale, especially, and then, well, his PhD was in Sherbrooke. The Institut Quantique did not exist at the time, but anyway, at Sherbrooke. Then went to Yale, and then went back to Sherbrooke after that time. And he's been working, and he's an extremely well-known name in in the field, as I can attest. And of course, we have special connection with Sherbrooke because Maya Garcia Berniori, who's here, is also currently there. And of course, for me, it's special because my former student was a postdoc with Sandra, Adrián Parra Rodriguez. So he's, as I said, a well-known expert. His review is, one of his reviews is material for the superconducting devices part of the quantum technologies course we are teaching here, for instance. You've got the floor. Thanks a lot.
Thank you for the introduction. Thank you for giving me the occasion to give a seminar here. Of course, indeed, there's a connection with Bilbao, as was said at a former postdoc who was here, and of course, I've been following the work, which has been done here for many years. I'm also especially happy to see there are undergrad students. How many are there? Can you? Okay, well, this talk is for you. That's what I'm saying. Okay, so this talk is for non-experts, and my goal is to tell you about superconducting quantum processors. But let's start at the beginning. I cannot assume that you know what quantum information is, so let me say a few words about that too. Okay, maybe you know. Do you have? Okay, perfect. So. Yeah, let's start really at the beginning. Of course, these two giants, Niels Bohr and Einstein, that we see here in one of their debates about the nature of reality, essentially, the interpretation to give to quantum physics. Their goal was not to come up with technologies, right? Their goal was not to make any device or anything better. I mean, if we had told them to make something better, they probably would have worked on making, I don't know, better candle wax or something like this, right? And so, yet, as we know, that fundamental research has led to major outcome with that major effect on our society. Has transformed the world, really, from the GPS with their atomic clocks, medical imaging, and lasers. These are all innovations that come from physics labs. Right? This is all from physics, from quantum physics specifically. And the same is true from our current computers, classical computers, whose brain, the CPUs, is based on semiconducting devices. And to understand how to go from a piece of silicon, like semiconductor device, and to go to transistors, something that can encode and manipulate information, quantum physics was required. And so quantum physics is not only, therefore, the most fundamental theory, the most precise theory that we have to understand nature, it's also a theory that has transformed the world. And so as physicists, we can be very proud of that, and maybe we don't say it enough, the impact that we have on society. But what we know now in the last few decades is that we can go much beyond that. If we use more actively some quantum effects, interference, entanglement, superposition, then we can arrive at technologies that are otherwise impossible. And so there are several emerging quantum technologies, quantum computation, sensing, and communication. Here I will, of course, focus on quantum computing. But to understand how quantum can speed up calculations beyond what I said about using semiconductors for current computers, it's important to go back a little bit to how these computers work, very, very briefly. And of course, you probably all know, but it's still worth saying that these devices are only machines that deal in zeros and ones, right? They manipulate zeros and ones, billions of zeros and ones, each of them encoded in one of the billions of transistors. These machines have probably, I don't know, 15 billion transistors now in a centimeter square, something like this. Absolutely amazing technology. But each and every one of these zeros and ones, of course, can take one of two values, 0 or 1, right? And what we know now is that, and what we can realize in the lab now, test and measure and control very precisely, are new kind of devices, quantum transistors, that we call quantum bits or qubits, that can take the value 0, that can take the value 1, but can also take values that have no analogies. So for non-experts, we can call this 0 and 1. For the experts, we're maybe a little bit uncomfortable with this, right? What we really mean is a superposition. You've taken quantum physics so far, right? So I want you to think about a quantum superposition here. And yeah, we have to be a little bit uncomfortable when we say 0 and 1, but okay, that's fine. And so now, I mean, these devices exist, we can manipulate them, and my goal in this talk is to tell you how this works, how we can do that, how does it work, and what are the challenges that we still need to overcome if we want to make not just demonstration devices, but actually useful devices using these ideas. But of course, again, just to make sure that for the non-experts in quantum information, maybe there's a point that is important, is this notion of quantum parallelism, or what does it give you to go from or to and, right? What does it give you to operate a cube, not just a classical bit, which can take two value, but a quantum bit which can take superposition, all the values in between 0 and 1. And of course, the basic idea is only in this slide, where if I have a single qubit, it can take the value 0, as I said, 1, and that superposition 0 plus 1. If I have two qubits, then of course there's each of them can be in a superposition, which means that I have 4 possible values, and so on. 3 qubits, 8 possible values. That's here a uniform superposition, but I can have an arbitrary superposition with arbitrary coefficients in that superposition. And then you can ask yourself, okay, this is great, to encode that superposition, I can have a quantum computer with 3 qubits that realize that physical state, that superposition. But what would it require for you to store the same information in a classical computer? Right? To store the same information in a classical computer, you would have to store these 8, or minus normalization, but let's say these 8 complex coefficients, right? That is the cost of knowing, of encoding all of the information that you have about this state. And so if you have n qubits, that means that you need to store 2 to the n coefficients in your classical computer. And 2 to the n, as you know, is a number that grows scarily fast, right? Let's take an example. I have a quantum computer with 300 qubits only. It's a tiny machine, right? There are demonstration machines now with approaching 1,000 qubits now. So let's just take an example of a machine that has 300 qubits. That means that there are 2 to the 300 coefficients that represent the full quantum state. And if I want to write this down in a quantum computer, that's the number of bits of transistors that I would need. But just to give you let's try to imagine how large the 300 is. So just to get you there, 2 to the 300 is more than the number of drops of water that there are in the planet, in the oceans of the planet. But this is really just to give you the feeling of where we're going, because that scale is really off. 2 to the 300 is in fact larger than the number of atoms in the visible universe. And so that means that if you use all of the matter of the visible universe, all the atoms that are here, that form the planet, the solar system, I mean, everything that you see with our most precise telescopes now, you would not have, and you would declare that each of these atoms, right, is a transistor in a classical machine. You would not have enough atoms to build a machine that stores the information that are in these 300 qubits. Okay, so that's the key idea here. That's when we start to imagine what is possible, what is impossible to compute. Going from classical to quantum really changes this boundary. It's not just that you are speeding up some calculations, it is really that there are some computations that would be impossible otherwise, that are now possible if you use quantum effects, quantum physics. And that superposition, the superposition of all these values, but also interference and entanglement to do actually useful calculations. Okay, but the question now is, great, but how do you actually do this, right? How can you do this in the lab? And that's the question really that I want to answer in this presentation. There are different architectures to explore, to realize in the lab these ideas. They come under the name of superconducting qubits, trapped ions, spin qubits, neutral atoms, photonic qubits, and others. At the Institut Quantique in Sherbrooke, we study 3 of these different approaches. And there are also numerous companies, of course, around the world exploring these ideas. And this is just a subset of the companies that exist. But you will recognize brand names like IBM, Google, AWS, Intel, and so on. And so there are brand names, but there are also many startup companies around the world that are exploring these ideas. And just to make a little bit of publicity for what's happening in Sherbrooke, we have a startup hub in quantum where we have about 15 companies that are exploring superconducting qubits, spin qubits, neutral atom, photonic qubits, but also how to operate these machines, how to do useful quantum algorithms on these machines. I'll be happy to tell you more about that if you're interested in a second. Okay, but since my specialty is superconducting qubits, let's do a deeper dive on this topic. Just to tell you at the start, like the state of the art, and then we'll open that box and try to understand how these machines work at a more detailed level. But first, there's a web page from, you don't see the URL at the top, but that's like a screenshot from Safari, from some web browser. You can go to some web page by IBM and log in if you have an IBM ID, which you can create for free. And once you log in, you see something like this, which for the experts will recognize, let me go up here, which will recognize essentially the basic programming language of a quantum computer. Each of these lines, unfortunately you don't quite see the lines here, but there are lines. Each of the lines corresponds to different qubits, here 5 qubits, and each of these boxes correspond to different operations that you apply on these qubits. And you can simply drag and drop this, and then you can press set up and run. And then you can run this on a simulator, but you can also run an actual machine. That is in some dilution fridge. For most of the devices are in Yorktown in the US, but there is also one in San Sebastian, there is one in Bromont, which is just outside of Sherbrooke, and so on. And these machines where you can run do not only have 4 or 5 qubits. In some cases, they have up to, in that case, 127 qubits. The newer machines have 156 qubits. And of course, my favorite one is IBM Sherbrooke. It's not located in Sherbrooke. They just name the devices on cities. So we were really happy that they chose Sherbrooke. But that shows you the complexity of these devices. Each of these dots represents a qubit. Okay? And each of these links represents a connection between the qubits. And my goal is that at the end of this talk, you will understand what are these circles and what are these links. Okay, that's where we're going. But that just that picture demonstrates in a way the state of the art, the fact that this is, yes, very much fundamental research. There's a lot of development that has to be done, a lot that we don't understand and that we need to improve to make actually useful machine. Yet this technology is robust enough that it can be operated on a cloud, and non-experts can just log in, start programming, and execute increasingly complex quantum algorithms. Not yet truly useful quantum algorithms, but still increasingly complex and interesting. If these machines do not have yet value to generate for the economy, for companies, they have value for science, right? They are starting to be really interesting scientific tools, and that, to me, is already a success. You will also have heard, maybe, that back in 2019, Google has claimed to have reached, with the same type of approach, they have claimed to have reached what they called at the time quantum supremacy, quantum advantage. The fact that their machine could compute faster than any supercomputer some specific problem. In that case, it was some specific task that they asked their quantum processor, small quantum processor with, in that time, about 50 qubits, which the quantum processor could realize in about 3 minutes. And they had estimated that the fastest supercomputer in the world would have taken 10,000 years to do the same task. We'll come back to that claim later in the presentation. Okay, but now let's open that box and try to understand, like, how do these machines actually work? But first, what do I mean by quantum processors? What are the ingredients that go into these machines? Well, first, I've been talking about qubits, so you better have some qubits. Each qubit will encode one quantum bit of information. Essentially, what you want is a two-level system where you can store information in 0, 1, or in superpositions or in 0 and then 1. And so you probably want a lot of these qubits. I've talked about 156 qubits with the newest IBM machines. Of course, in practice, we may want millions of qubits, right? So we're quite far from the end goal. As I said, you want to be able to prepare interesting states of each of these qubits, and so for that you need single qubit gate control, and I'll come back to that. But you need a way to prepare 0, prepare 1, prepare superpositions. Qubits by themselves that are not talking to each other are interesting. You need to be able to prepare entangled states of these two qubits, states that have quantum correlations between the two. This is not dissimilar from a classical computer where, of course, you can do NOT gates that would change the value of every bit. But to do universal quantum computation, you need to have something which is called a NAND gate, a gate that compares the value of 2 bits and gives you something out depending on the 2 bits at the input. And so these entangling gates are now what are required to do these non-trivial multi-qubit or multi-bit operations. And of course, at the end of the day, you need to extract the information. If you don't read out, it was not useful to do the calculation to begin with. Okay, so that's the challenge, and it's a pretty big one, because on the one hand, you could think that there's really conflicting requirements here, because intuitively, you could imagine that, or you can understand intuitively that these qubits must be isolated from everything else, right? Because like the classical world, which is in interaction with its environment, about the photons, and phonons, and so on, is acting very classically. So what we want are objects that are isolated from everything. In this way, they will be able to maintain these superpositions for a long time. So from that point of view, a neutrino is the perfect qubit, right? It doesn't interact with anything. So neutrino, perfect qubit. However, a neutrino is also a very useless qubit because you cannot interact with it. And so you cannot operate it, you cannot measure it. So you want a system that is both uncoupled to everything, but also strongly coupled to some part of its environment, because you want to act on it and you want to act on it fast. And so satisfying these two requirements, contradictory requirements, is the challenge. But it's also why this field is so much fun, right? Because it's difficult physics, it's beautiful physics. Okay, so how do we satisfy these contradictory challenges? In superconducting processors, one approach that is used by Google and IBM and others is something which is called circuit quantum electrodynamics, where we mix something which are called transmon qubits and microwave cavities. So let me define all of these words. So the essence, essentially, is that we will place these qubits that in a minute I will explain are transmon qubits. I will have to explain what they are. But these transmon qubits are essentially electrical circuits that have a 0-1 transition frequency in the gigahertz range. Okay, so about 5 gigahertz. Okay, so anything above a few gigahertz for me is high energy physics, right? Okay, so like above 20 gigahertz, that's like way too high. The gap of aluminum is 80 gigahertz, right? And so that is really, really high energy. You don't want to go there because you will break things. So about 5 gigahertz. And so all of these objects here are microwave sources that, as we will discuss in a second, that control the state of the qubit. I'll tell you more about that. And now I've added this object, which is a cartoon for a microwave cavity. So these are a cartoon for two mirrors that are facing each other, and they form a high quality factor cavity, which can store photons for a long time, but here, microwave photons. And why is that a good thing to have this microwave cavity? It's a good thing for two reasons. First, you can drive the input port of the cavity and collect what comes out at the output port. And the signal that is transmitted will carry information about the state of the qubit. Okay? As a result, you can measure the state of the qubit by measuring the transmission. To give you an intuition, there's two intuitions that I can give you. First, more electrical engineering intuition. These qubits are electrical circuits. They have some impedance, but the impedance is qubit state dependent. As a result, the transmission will depend on the impedance that is presented to the input port and the output port, and therefore the transmission will depend on the state of the qubit. The second intuition I can give you is that if this was an optical cavity and you put a piece of dielectric in it, of course that will change the transmission, right? But now what we're saying is that the dielectric constant depends on the quantum state, right? And so by putting different types of dielectric, the transmission that you measure will change. And from that, you can infer the state of the qubit. So this is called a dispersive readout. The second reason why using a microwave cavity is interesting is because maybe you prepare some interesting state of one of the qubits, and you want that qubit, that information to be shared with some other qubit, right? In these entangling gates I was talking about. And so what you can do is you can transfer that information from the qubit, the left, for example, the leftmost one here, to a microwave photon stored in the cavity. It's an IQ cavity. That microwave photon will be stored there for a long time. There's enough time to transfer that information to another qubit. And this way you can do, non-trivial interactions. In particular, you can entangle qubits. And something that is interesting is that these qubits do not have to be nearest neighbors. They can be pretty far apart. And I will show you examples later where these qubits are really, really far apart and these interactions can be made. Okay? By the way, please stop me for questions. I don't know if it's the usual approach, but don't hesitate to stop me for questions anytime. Okay? Great. So these cavities can take several shape and form. These microwave cavities are essentially some harmonic mode. And you know that you can have an harmonic mode made out in circuits made out of an LC circuit, right? An LC circuit is an harmonic oscillator, so that's a simple way to make these cavities. You can have literally a 3D cavity in which you place a qubit, or as I will show you in a few minutes, you can also make a cavity out of something which is called a coplanar transmission line. Essentially, it's a little piece of aluminum about a centimeter long, right? Why a centimeter long? Because that's the wavelength of microwave photons, right? If we're talking about a few gigahertz, the wavelength is about a centimeter. And so just a piece of aluminum wire evaporated on a surface, again, I will show you this in more detail in a second, of about a centimeter, is essentially like a guitar string, right? It has boundary conditions. There's no current that flows outside of that finite piece of wire. And as a result, just like a guitar string, which has boundary conditions, it's fixed at the two ends, it has modes, it has normal modes. And these normal modes are the harmonic oscillators that we use to store quantum information in these resonators in which we store photons. Okay? And here I'm showing this with some wiggle, just because we want to, maybe a centimeter is too long for your chip, you just want to compress this a little bit in practice. The length is still a centimeter, but it takes less space. Okay, that's a detail, but it will become important in a second. That will help you in a second to understand what you're looking at. And so what are you looking at? And so you're looking at a chip here, which is a bit of a dinosaur. It's a chip which was given to me by my friend Andreas Wallraff, which is at the ETH Zurich. And that's the chip that I have here. And so what I will do is that I will spend a few minutes talking about this, but I will just pass it along in the audience. And there's two rules with that, and one suggestion. The first rule is take it by the edge, like this. If you put your finger on the copper, you will leave a fingerprint, and then I'll know that you've put your finger on the... The second rule is that it has to come back to me at the end. And my recommendation is that you look at it, you look at light passing through this thing. Okay, so let's do that. Great. Okay, and so maybe look from the other side also. That's the other recommendation. Okay, so what are you seeing here? So first, you see a bunch of connectors, right? This is where microwave signals will come in, right? You literally have coax cables that come in. This is where the signal comes in. You have little waveguides that are here that you can see. There are little lines. And this is just to transmit the microwave signal from the connectors, from the outside of the fridge, to the chip, which is in the center. The chip is, in that particular case, a piece of sapphire. Silicon is also more common now, but this is sapphire, and on which was evaporated a thin film of aluminum. Okay, aluminum is superconducting qubits. If you will see, I will ask you to comment on this in a second, but on this chip, there are devices that look like this. Okay, and what is this? So this is a transmon qubit. So first, everything that is dark is the sapphire. Not so interesting. Everything that is, well, not everything, but these, which are, I don't know, pink, beige, something, these are ground planes. Okay, so not super interesting also, but really important. You have transmission lines here, which are really connected to these coax cables. And what do you see? You see in white, this is again aluminum, just colored differently to make it easier to see. And what do you see? You see first something that is pretty big, 300 micron, right? So that is a big quantum object. So that object is made out of two pieces of aluminum that are facing each other. So there's a name for that. Maybe the students want to say something. If you have two pieces of metal that are facing each other, what is the circuit element corresponding to that? It's a capacitor. Yeah, so it's a capacitor. Great. So a transmon is mostly a capacitor. And then there's a wire here. And just a wire which has no resistance because it's superconducting, no resistance to the flow of electric current, will have one property. It's not a capacitor, it's not a resistor, there's pretty much only one choice. Maybe you want to try? I don't know, sorry. I don't know, sorry, I don't want to stress you out before exam, so it's an inductor, essentially. It has some inductance. So what are you seeing? You're seeing something which is essentially an LC circuit. It's a capacitor that's shunted by an inductance. That's it. So for the people who have, the person that has the chip, so how many qubits are there on this chip? So how many qubits do you think there are? Do you see? I want the answer from someone else first. Yeah, there's 4. So you see 4 corners. I hope that you noticed that. The others, there were like four like distinctive places. That's an old chip. It has only 4 transmon. As I said, it's a bit of a dinosaur, but okay. Excellent. But first, okay, let's go back to this. Is this a good qubit? Right? Can you make a qubit out of an LC circuit? Well, no, right? So it cannot exactly be that. And the reason why it cannot be that is that if you look at an harmonic oscillator and you quantize it, it's an harmonic oscillator. So it has discrete levels. Each of these discrete levels corresponding to one quantum excitation of the electromagnetic field, right, of this object. And a quantum of the electromagnetic field has another name. It's called a photon, right? So that circuit, right, stores photons, right, but microwave photons in the circuit elements. And so you have state 0, 1, 2, 3, etc. But the problem is that that separation is the same everywhere, right? It's 1 over square root of LC. It's the LC frequency. And so how do you control now the circuit is that you, say, prepare it in the ground state. You can prepare it in the ground state easily because, as I said, 5 gigahertz is high energy physics for us. So because we operate at 10 millikelvin, right? At 10 millikelvin, that corresponds to, I have a blank suddenly. 10 millikelvin is, what is it? I forget in gigahertz. I don't know why, about 1? Yeah, about 1, huh? Yeah, 50 milli, yeah, that's right, thank you. 50, that's why I chose 50 because it was 1 gigahertz, thank you. But we operate 5 times lower than that, right? And so there is no enough thermal energy to promote the system from 0 to 1. So if you just let it relax, it will go to its ground state. So preparing the ground state of the system is easy because it's high energy compared to the thermal bath. But okay, now you want to control this, and the way you will do that is that you will hook up, okay, so it looks like sorry, I forgot this. I thought that I had something else here, but that's fine. Okay, so the way you will control the system is by first preparing the ground state, and then sending, if you had an atom, you would send a laser pulse, right, to do a transition between orbitals, between S and P. Here you will send to the appropriate connector here that terminates at the appropriate place. You will send a microwave pulse, which is the equivalent of a laser. And that microwave pulse will be able to promote the system from 0 to 1, just like in an atom with a laser. So excellent. You can do something like this. And in principle, you could do Rabi oscillations between 0 and 1. But that is only true if that level 2 wasn't there, right? Because in the presence of level 2, right, what happens is that once you drive run transition and you continue driving, the system will go up, but it will also go down, and it will end up exploring all of the Hilbert space. In short, you'll prepare a coherent state, a superposition of different possible values of the photon number. That is really bad because you wanted to restrict your system to the first 2 states. And so what you need is to break the nonlinearity. You need to have a ladder that is nonlinear. And fortunately, there is a circuit element that does that. It's called the Josephson junction. And so that wire is in fact not just a wire. At this place, there is a break in the wire. And so the wire comes in, there is a break, and you've oxidized this wire, and then you continue the wire in a different layer. Essentially, at that point, you have a sandwich between the superconductor, an oxide, and a superconductor. It looks like this in practice. So this is the one wire. which you've oxidized, and then added this other layer on top. And so at that point, you have a sandwich superconductor, insulator, superconductor, working with aluminum, so aluminum, aluminum oxide, aluminum. And that element is also, it's called a Josephson junction, and that element is close to an inductance, at least in the appropriate regime we're thinking about here. But it's an inductance that has the property that it is nonlinear. So rather than having a potential energy, an energy that is quadratic, it has, funny enough, a potential that is has a cosine shape. Okay, so the current phase relationship in a Josephson junction is not only proportional to the inductance, but it's proportional to something like an inductance, but with a nonlinear function of the flux. What does that mean? What does that give you? That means that the energy separation between 0, 1, and 2 will be slightly different. So in practice, 2 will be slightly below what it would be if it was a harmonic oscillator. If the 0-1 transition frequency is 5 gigahertz, the 1-2 transition frequency is 5 gigahertz minus about 100 megahertz. Okay, so it's a tiny, tiny effect on the range that we're talking about. But that effect is large enough. Now that means that we can really think only about the first two states. And if you're careful enough, you can prepare the 0 state, prepare the 1 state by connecting the system to some microwave source, which is essentially a microwave oven, but is much more fancy, costs $50,000 each, and can produce very precise pulses of the microwave. You can prepare a superposition of these two. You can change the phase of the superposition by playing with the microwave tone. And in the end, you can do universal control of that qubit simply by shining microwaves at the appropriate point. Excellent. Now, you can also notice that there is multiple connecting lines here. I've talked about these. There is one line, in fact, I've talked about this one and that one, sorry, not this one yet. So this one is the microwave resonator I was talking about a minute ago. And so now for the person who has the chip, if you look at it, if you look at the chip again, if you see the 4 qubits, do you see some kind of wiggly line that is connecting the qubits? On the other side. You see something that looks like the wiggly line I was drawing before? Maybe not. But okay, so have a look again if you didn't see first. And so there are resonators on this chip exactly to do the readout that I was talking about. There is, however, yet more wiggly lines. Yeah, so maybe something that looks like this now, right? And so, as I said, there are 4 qubits. So every pair of qubits is also connected by one of these wiggly lines, okay? And that is the way that you can do entanglement. You can share information between the different pairs of qubits, okay? And so what do we have here? So that's the basic idea of circuit quantum electrodynamics, circuit QED, which takes its name because it's the interaction of light, the photons that are stored in the microwave resonator, with matter here, the artificial atoms that are the transmon qubits. Okay, these transmon qubits are really artificial atoms. They have the properties of atoms. This is how you should think about them. With this wiggly line, you can do the qubit gates, and this way you can create entangled states of 2 qubits that are separated by centimeter, right? And so what you're doing is you're taking objects that you can see with the naked eyes, right, 300 microns. You take 2 of them that are separated by a microscopic distance, and you can prepare the most quantum state possible, right, entangled state. So, I mean, that's, again, for the students. If you think that quantum physics is the physics of infinitely small, right, that is not the case, right? Quantum physics is the physics that emerges in the right conditions. And these are some right conditions for quantum physics to emerge. You can do these experiments by separating the qubits to be not just a centimeter apart, but the group of Andreas Wallraff, who gave me this chip, has also done an experiment where there's not only one dilution fridge. This is the apparatus that goes to about 10 milli-K in which the qubit is stored, but two of these qubits, right? Two of these fridges, and each of the fridge has one qubit. And there's a tube that you can see in between the two fridges that has essentially a long transmission line, a 5-meter transmission line that is cooled down, okay? And you can exchange a single photon emitted by one of these qubits, traveling down the transmission line, absorbed by the second qubit. And if you instead send a superposition of a photon and no photon, 0 plus 1 photon, in the end, you absorb and not absorb the excitation here, and it's where you prepare an entangled state between the two qubits that are 5 meters apart. So this is something that was reported back in 2020, and yeah, because Andreas Walraff can do that, they've also done that with two fridges separated by 30 meters. And for the experts, now that you are at 30 meters, you can start looking at violations of Bell inequalities without loopholes. You can close the locality loophole because of the separation. So that now almost looks like an high energy physics experiment. And you cannot see the fridge. There's a fridge somewhere in the back there, and there's another fridge. It's just very difficult to take a picture of something that is 30 meters long. But okay. But let's go back to processors. So I've shown you, and you've seen a chip with a few qubits, but more modern chips have more qubits. So this is a chip from IBM, about from 2015. That's a chip, in fact, that's probably the last device that you can see where IBM showed us a device. Now they don't show us devices anymore, but yet we can look at this. And what do you see? I think you will see, I hope, something that you will recognize now, because there are clearly wiggly lines, and there are like things facing each other, right? And so what you have are 16 transmons that are organized in these two arrays of 8 and 8. You have coupling resonators between each of some pairs of transmons, and you have additional wiggly lines here, which are the readout resonators. So in this particular implementation, there are resonators for coupling, and there are resonators for readout. And so what does that give you? That gives you a structure which looks like this, right? Each of the dots is a transmon qubits. Each of the line is a coupling resonator. And so when I was showing you the device with 156 qubits, this is what you were looking at. You were looking at transmons coupled via resonators. Okay, so you have a better idea of how it looks like. Now, there are different ways the transmon do not have to be just parallel plate capacitors. There are different shapes for these capacitors. This is a device by Rigetti, again, probably the last one that we can see from them, where the transmons are these Mickey Mouse type objects. This is a capacitor. You can draw a capacitor in any way that you want. For some reason, for them, that was a better choice. Now, however, when IBM shows us a device, this is what they're showing us, right? It looks like a product that you can put in an iPhone or something like this. Yet, this is super impressive technology because, so this is a 120 qubit device. Now, as I said, they have 156 qubit devices, but these devices are starting to be very complex. They are multi-layered devices, meaning that there is multiple substrates on which each have different functions. So, for example, there's a layer for the wiring, just to bring the signals. If there's a qubit in the middle of the chip, you need to bring signal to that qubit. So there's a layer for wiring. There's a layer for the measurement resonators, and there's a layer for the qubits. Okay? And each of them are coupled via something which is called silicon vias, which are essentially little holes that are punched through the substrate and are metallized, and this way you can send signal through substrates. Okay? And so this is far from a functional quantum computer, a useful quantum computer, but still it's impressive technology being put together using these ideas. And so, again, when I showed you this device, now I hope you understand what you were seeing, right? Each dot, again, is a transmon qubit. It's this nonlinear oscillator. each of the coupling element in this particular device were indeed resonators. Excellent. I've also told you that Google claimed to have achieved quantum advantage with that device, with a similar device. In that particular case, that was 2019, in that particular case, the device had 55, 53 qubits. I think there was one qubit that didn't work. In their particular case, so the qubits are represented by these crosses. So for the capacitance turned out to have a cross shape, doesn't matter. And the coupling elements are not resonators in that particular case, but they are active elements that can turn on and off the coupling more efficiently. They turn out to be other transmons, in fact. So it's a large grid of transmons coupled by transmons. And this is how you can control and turn on and off the interaction more efficiently than in the IBM architecture that I showed you. So I said that I would come back to that claim. So that's the claim that you could do with this 53 qubit device, a computation in 3 minutes that would have taken Summit, at the time the world's fastest supercomputer, 10,000 years. That claim was rapidly debunked, however, using matrix prog state approaches, tensor network approaches. You can simulate that experiment in a few seconds on your laptop. Okay. So what's happening now is that there's a race between quantum processors and classical processors where there are claims, and then someone comes up and says, hey, I've invented a new classical approach to use a supercomputer or even my laptop, and I can do better. And so that race is going on, and it's quite interesting. The fact that there is that race is itself interesting. You have to remember these processors are almost artisanal processors, right? They are made by relatively small teams. Google at the time had probably 150 employees working on this, which is, I mean, when you compare to the semiconductor industry that led to the creation of the world's the fastest supercomputer, is a tiny thing, right? The integrated investment in classical computers is trillions, tens of trillions, I don't know how many. And we're comparing here to technology that is pretty, still very developing. So the fact that we have even that discussion is interesting. But things have changed a little bit in 2024, where again, Google, now with their Willow processor with 105 qubits, have now claimed a separation between classical and quantum, which is not 3 minutes to 10,000 years, but 3 minutes, or maybe I think 5 minutes to 10 septillion years, 10 to the 25 years. So that separation is starting to be large. As far as I know, nobody has been able to close that gap with classical methods. My feeling, I'm not an expert in the classical methods here, but my feeling is that closing that gap starts to be a difficult proposition. And so maybe this is an actual quantum advantage, but this is not something that can actually be proven, right? Yeah. About nothing. So what was the computation about? That's a very good question. It was really about nothing. So that's a key point. So the Google researchers developed an algorithm whose only role was to show this separation. It's a sampling task. Essentially, the quantum computer can prepare a distribution. So if you're measuring outcomes from you prepare some complex state, you measure, and you get some distribution of bit values. And the distribution that you're sampling is a distribution that would be extremely difficult to reproduce on a classical computer. That serves no purpose except showing that separation, right? And so we have to work on actually useful quantum algorithms. But there's also some progress. Google and IBM have shown, and others working with them have shown some interesting results, but maybe not with that type of separation, however. So, but it's starting to be a useful tool. How much more time? Should I stop here, or how much more? There's a last 5 minutes? Okay. So I think the key message here is that if you just put all of these devices together and I put more of them, that will not lead to something useful. That will not lead to useful technology. That will not lead to what we call fault tolerance. A quantum computer that can correct errors and maintain coherence, maintain a coherent quantum computation for a long time, as long as necessary to do universal quantum computing, any task that you could throw at a computer. And so we need really to focus, or rather the field now is really focusing on quantum error correction, that is correcting the errors that are occurring in these devices. And let me tell you, like in the last few minutes, what this is about, and then that's all, I'll be done. So first, if you have a single qubit, so this is my artist representation of a superposition of 0 and 1. I've done my best. And that is the outcome of some complicated calculation, say, right? And suddenly, you really care about the value of that qubit, but suddenly there's an error, everything is lost, right? And by the nature of how information is encoded in quantum states, the qubits are prone to errors. That is very different from classical bits. It can only take the value 0, it can only take the value 1, there's nothing in between, and flipping from one to the other is very difficult. In a quantum computer, having small errors is a thing, right? You can go from almost all 0 to a little bit 1. 0, almost all 0, and a little bit 1, right? So there's a continuous nature to the quantum information, and that leads to errors. This is something which is understood from the beginning, and the cure to that is something which is also understood. This is error correction. And that cure is not so complicated on paper. No, that's not even true. That cure is the following, is to use redundancy. And that's the same in classical physics, of course. If you send a message and you imagine that there will be an error, well, just send many copies of that same message. If there's an error in one, you do a majority vote. You look at the 3 bits, 2 are the same, 1 is different. You say, well, probably there was just one error. I know what the outcome is. And so you can do the same thing with quantum information. Well, of course, because measuring quantum state destroys the quantum state, things are much more subtle, much more difficult. But yet, redundancy can be used to protect quantum information. But the question is, how much redundancy do you need to actually build really protected qubits? And the answer, it looks like, is a lot. So what I'm saying here is that the concept here is that we will have physical qubits, and that chip has 4 physical qubits, right? And these 4 physical qubits, or maybe thousands of physical qubits, will be used together as a single logical qubit, right? And error correction will be implemented within that logical qubit. And then you expect no errors on this one. And then if you want to do a useful quantum computation, you will connect logical qubits, which are each 1,000 maybe of physical qubits, and you'll do logical operations on these logical qubits, right? And so that means that you need tons and tons of qubits. And so protecting a single qubit from errors may require thousands of physical qubits. And the number you need changes with the quality of your qubits. If you have qubits that make a lot of errors, you may need a lot of physical qubits. And so, for example, if you want to factor a 600-bit number, that may require something like 10 to the 3 logical qubits, and that may need 100,000 to a few million physical qubits. Interestingly, I need to change the slide almost every month now, because these numbers go down, right? Last month, that I had written 10 to the 6 to 10 to the 9. And now the estimate has gone down drastically. There's been a bunch of really interesting research on the algorithm side that has shown how to use less logical qubits and physical qubits to do the same task. And so that's quite interesting. The requirements go down and the device improves. So at some point we may meet. But that means is that we really need better physical qubits, better gates, better readouts, better codes to make that a reality. I could stop here or flash 3 things, but I'm happy to stop here if you... I'll just flash the first steps in doing these experiments on error correction. So I can flash results that were obtained with the ETH Zurich, again, the same group that provided this chip, where we have realized the first experimental realization of what is known as the distance tree surface code. This is one possible error correcting code. It's the most commonly studied error correcting code. And to correct a single error in that particular code, you need 17 qubits, 17 transpond qubits, which in this device are these yellow stars. Okay, you can again make capacitors any shape for that particular device. The star has the good shape. In that qubit, it was supposed to do 16 rounds of error corrections, preserving quantum information for 16 rounds. However, the quality of the logical qubit that was created in that experiment was worse than any of the physical qubits. So doing error correction was worse than useless. Okay? But that was still an interesting, important first step. It was important to show like, yes, okay, these ideas can be, then they work in principle. But if you add faulty objects, and if these objects are too faulty, they will just create a logical qubit that is more faulty, right? Adding faults can make things worse. But we knew that from the beginning. It was impossible that a code that corrects for a single error would lead to a better logical qubit. So that we knew from the start. Yet, that experiment had to be done. Since Google has repeated this, now not with 17, but with up to 100, right? And because that qubit could correct more errors, they could finally show a logical qubit that was more robust than the physical qubit. And they could do, in their case, 250 times the round of correction. But that is very scary, right? Because imagine that you need a plaquette, which is now, so each of these objects is a qubit. Now maybe you need 10 times more qubits, right? 1,000 qubits to protect the quantum information. And remember what each of these are, right? They are transpond qubits. There are some couplers in between. And you need microwave generators to control each of these. What is the cost of a microwave generator? About $50,000, maybe $20,000, maybe $10,000 if you... So we're talking about machines that could cost billions of dollars just of classical electronics around them, like extremely scary. There's another path, and I will finish with that. There's another path, and I'll do publicity for some of the things that are happening in Sherbrooke here. There's another path which is called hardware-efficient quantum error correction, where rather than having redundancy in numbers of qubits, the redundancy comes from encoding the information in the microwave cavities itself. A microwave cavity has, in principle, infinitely many number of levels. There is intrinsic redundancy in that structure. And so Narcomantic is a company in Sherbrooke that is using this approach. Not necessarily to go into the details, but they have shown, even before Google, this concept of a physical qubit being more robust than the physical components out of which it is built. And in their case, a single device is a single logical qubit, so a single microwave source rather than 1,000 maybe. So that's a promising route. It's a difficult route because building a quantum computer is difficult, but it's a different one. Oh yeah, and with that, right, I've been talking about technology and things and devices, but we have to remember, right, that this is coming from where this is coming from. The curiosity, the fundamental research, right, that is the basis of all of this. Yes, so again, that without that fundamental research and that curiosity, there would be none of what we're talking about. And that's really what this is about. And with that, I'll just flash this, and thank you for your attention.
Thanks a lot, merci bien. We do have time for questions, and I suggest you make questions because I will make too many.
Thanks for the talk. I have a question regarding these advances in error correction you commented on that have allowed, or in principle now, the amount of logical qubits you will need to achieve factoring has reduced substantially. But if I understand correctly, for that you need to build these logical qubits, you need long-range interactions. So is there a plan for superconducting circuits to be able to apply these error correcting codes maybe with cavity-mediated interactions instead of the nearest neighbor, or?
So yeah, good question. So there's been multiple work on this. There's work on based on the neutral atom architecture, where the number I think is 10,000 in that case, qubits, where there's long-range connectivity because you can move atoms around. In superconducting qubits, they are fixed in space, of course. However, my understanding, and honestly I could be wrong there because I didn't read carefully that paper, but there is one work from Google that claimed this 100,000, like 10 to the 5 number that I gave there, where my understanding is that they use the surface code without long-range interactions. And so I could be wrong with this, but that is my understanding. And so that number is maintained even if there's only next nearest neighbor interaction. That being said, there is work on long-range interactions. They exist, they have been demonstrated. IBM is not betting on what is called the surface code, what I talked about, but rather on quantum LDPC code, quantum low-density parity check codes, where you require long-range coupling, and they have already demonstrated that. The advantage of these codes is that you will require, in principle, much fewer physical qubit per logical qubit. And so they come at a huge advantage, but also at the price of requiring these long-range couplers. But this is really something that is just starting. If you had asked me this question maybe like 3 years ago, I would have said like, this is really difficult, like, I'm not sure this will happen. But in the last like about 2 years, there's been like really impressive experimental demonstration. So it seemed like this is fine, this can be done. So I'm not worried about that more than anything else. I'm worried about everything, I would say.
More questions?
Thank you for the talk. I have actually 2 questions. One of them is that people usually talk about the number of physical qubits for logical qubit, but not the number of physical operations for logical operation. How does this scale? Which is the state?
Okay, this is a little bit out of where I'm truly an expert, but for the surface code, so I cannot answer for quantum LDPC code. This doing logical operation is more complex and something that is still being developed. For the surface code, if you want to do a CNOT, what you need to do is something which is called lattice surgery. So what you do is you take two of these plaquettes. And so you have, imagine that's a logical qubit. You have a second plaquette like this, which is your logical qubit. And you need to add an array of qubit in between. And what you do are 2 qubit gates between the edge qubits of both plaquettes and the additional qubits. And doing this results in a logical control NOT operation. So that is, the cost is the length of this, which is not so bad, because it's not the area, it's just the length. So the scaling is not terrible.
But you don't need also some operations inside the plaquette?
Not for lattice surgery. Not for lattice surgery. If you want to do, however, a single qubit logical operation, then it's something which acts inside. Yeah.
And the second question is a little bit different. It's about which is, in your opinion, the limitation for scaling superconducting circuits in fabrication? Or...
what is the, everything, I would say. I mean, I will just write, maybe put this again. So I think this is my summary, right? Everything needs to get better. If you just push on the current technology without improving all of the components and the operation of these components, this will never work. And so we need better physical qubits. A question maybe is the transmon, like the qubits that will actually succeed in making a fault-tolerant quantum computer? That we don't even know, right? There are other qubits, for example, by a group that are being explored. And that has tremendous value because we just don't know if the transmon is good enough. What I can say, however, is there's been like super material development in the last few years, in particular by Nathalie de Leon in Princeton, who has recently showed transmon qubit with a lifetime of 3 milliseconds. That is absolutely, I mean, maybe it's, for many this is short, but this is a very long time for superconducting circuits. And so maybe there's hope. But still, like, everything has to be improved. Yeah. It's not a very precise answer, but I think that's the state of things.
Actually, along those lines, yeah, what about possible topological protected qubits, zero pi's, or kite-likes? Or...
Yeah, so there exist qubits that are more complex. The transmon is just a junction that is shunted by a capacitor. It has two nodes, right? There's the island on the top, the island on the bottom. You can make circuits that have multiple nodes, more nodes, and then you can connect junctions and inductors and capacitors in different topology. And that will lead to very different type of quantum states that are encoded. And in particular, you can make a qubit called a 0 pi that is, whose T1 and T2 can be extremely long on paper. Experimentally, it's been demonstrated to have 1.6 millisecond of T1. T2 was much shorter. However, the issue with these protected qubits is that they are a little bit like the neutrinos we're talking about at the beginning. They are so protected that they are protected against operations that we are trying to make. And so there's a tension between protection and fast gates. And there are proposals to make like truly protected, gates on these protected qubits, but they usually imply breaking the protections for a while. Maybe that's fine, but it comes at some cost, right? You do break the protection. But again, it's worth exploring these qubits because surprises may occur, right?
I have another question because, well, you did show some examples, Rigetti, some Google, some IBM. So if I remember correctly, IBM is moving away from the architecture they have with the heavy hex, and they are moving to a different one. That's a bit more for experts.
So the IBM machine has this very low connectivity where qubits are connected. There's only a few qubits that are connected. This is called the AVX lattice, and they had in mind some sort of error correcting code to justify that. But they're moving to a nearest neighbor coupling, just like Google is doing, because more connectivity that you have, there's more path for errors, more problems, potential problems. But at the same time, here there's so few qubits that can be entangled that it's very difficult to actually do something useful on these machines. Moreover, the LDPC codes that they're implementing will require more connectivity, so they don't have any choice.
More questions? I'm surprised. Jesus has a...
Maybe this question is a little related with the first one, but you mentioned this architecture where you have your qubits in a cavity, and I know that some companies are making an effort to try to make this like IQM, to couple multiple qubits to the same resonator and do resonator mediated.
Yeah.
What are your thoughts on this? Like, this could reduce the complexity a little bit of...
Right. So here there's qubit, coupler, qubit. This is what I've talked about. And what you're saying is that you could have coupling element, qubit, 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 qubit. They all talk to the coupling element, and then you can decide which pair is talking. This is, if they can make this work, it reduces the complexity for many reasons. Trivially, only because there's only one control knob rather than each of the couplers typically will need some line that you bring from room temperature down to the fridge, and that is difficult. So you want to be able to multiplex the signal. You want to be able to do many things with a single line. That achieves that. However, the challenge is that this can also mediate errors, right? Now, if you look, you have a bunch of objects that are coupled together. You need to look at the normal modes of that object. And if there is, the normal modes will be strange things. And if there's an error or something wrong happening here, that can have repercussions elsewhere. And so that's the thing I would be a little bit nervous about, but I'm sure they have that in mind when they're developing this. So I'm looking forward to see how it works in practice. So interesting on paper. Let's see if they can make it work like at really high fidelity.
Hi, thank you for the talk. My question is, I think, related with the one of Inigo. Before, I was going to ask you about this improving the physical qubits, right? So in terms of improving the simple ones like transmon-based, which is Google everything, or Fluxonium, etc., or that you also find interesting to explore these new, more complex architectures, which you already answered. So my question is, so then in the next step or the next improvement that you think we will be seeing in terms of improving physical qubits will be pushing the limits of Kornsteins in these simple architectures in terms of fabrication, materials then, or?
Yeah, so this I think is a super promising direction that not enough groups are pushing on. This is just very difficult material science. You have to deal with two-level systems, which are the plague of everything. And there's really Nathalie de Leon that is pushing on this, and she's able to do, she has also very small devices where she's testing these ideas, so 3 millisecond T1 time, relaxation times. But what is important is to achieve that in a processor, right? And in a processor is much more complex. You have much more, like everything is talking to everyone. There's multiple control lines. So translating these material improvements from like test devices to actual processors is extremely important and will require like all different line of effort that the type of people doing the material research are not the best to do, right? This is not what they do. I can add that Nathalie de Leon is now working part-time at Google, so let's see what comes out of that.
Sorry, I have a question. Oh, okay. So, I mean, okay, first, thanks a lot for the talk. I have a question regarding this error correction code because, okay, it seems that there is really some sort of two paths that we can follow in the sense, okay, have better qubit and have new qubit, start to do these sort of things. But something that I think that the people miss sometimes is that, for example, in error correction, there is this very strong assumption that the noise models that you have in your device are fixed, which in all those systems, because of drift, quasi-particle, or whatever, start to fail. So I don't know, you are in the plans to, for example, do more sort of active ways to keep track of how this drift is changing on time, such that you adapt the correcting code accordingly.
Yeah, so I'll answer your question, but let's moving a little bit to the side, but still answering your question. So at the moment, that's when I said better codes in one of the slides that we need that. What I mean by that is that you're touching that your questioning is touching that, is that at the moment, error correcting codes are developed by theorists that do not have a good understanding, a deep understanding of the physical system, nor the errors occurring on these physical systems. And so if now you realize that, in fact, about 99, I don't know, I'm not sure exactly what is the number, but let's say 90% of the clock cycle of a quantum computer will be spent doing error correction. Like, and on the side, it will manage to do a little bit of calculation. This is what we're talking about here. It's really an error correcting machine with a side quest of doing something useful. I think there's a better approach than that, right? We should develop codes with knowledge of the device, but also with knowledge of the errors that are most likely to occur on these devices. And then I want to come back to this hardware efficient approach, like for example, non-quantic, but they're not unique there. And that's exactly the point there. You look at the device and you say, what is the most likely error? And this is what you correct for. And you're not spending time correcting for errors that do not occur. And so that's why I really like this line of approach where, yeah, you're really informed by the physics to make the choice of the code. I don't know if that's answering your question.
But the problem is that from the solid-state physics, frequently we do not have a very good knowledge of what the sources so far, all this kind of about TLS and what have you. It's still very murky. So you are claiming we should do a phenomenological characterization of the predominant error form in a particular device.
Absolutely correct. So these devices are complex. There are many sources of errors, and we do not understand everything. TLS, I don't know if we'll ever understand. That's a different question. But to come back to this hardware-efficient approach, the key there is to use a very simple system where the information is encoded in an oscillator, and there's not many things that can happen in an oscillator. It can lose a photon, essentially. And that's why this idea works. Indeed, if you take a very, very complex system and you try to use these ideas, that becomes very difficult because your knowledge of what actually are the error sources will go down, and therefore your capacity of designing the right code will go down. So absolutely.
Actually, the next question is, as a matter of fact, next week we are going to have Ramon Aguado give a talk about transport in hybrid semi-superconductor structures. So hybrids, do you have any feeling?
So interesting. So sometimes it's sold as, okay, we will need to have a fast qubit which has a fast clock cycle to do operations, and maybe a slower but higher memory qubit for the memory. That's an option that's being explored. My intuition is that there's a large cost in shuffling information around, and so it's probably better to just keep improving everything and making fast qubits with long relaxation time, coherence times. That I feel like a device with a monolithic device will, not monolithic, but single species device. That's my intuition at the moment. But again, a key point is that it's worth exploring all of these options because we do not know. So it's absolutely worth exploring all of these options.
Thanks for the talk. You have been talking about these limitations. For example, one is implementing these error-correcting codes. But what happened after that? Imagine that we can implement that. Can we implement classical decoders that are efficiently for this type of codes that we are trying to implement, or this is a limitation right now in the field?
I mean, that's certainly, so decoding is the act of, okay, if you have a lattice of qubits, of physical qubits, right, and then an error has occurred, and you need to correct it. But before correcting it, you need to figure out what error has occurred, right? And so you will have a bunch of additional qubits here. You have a bunch of qubits in these lattices, not additional, but a bunch of qubits that are used to compute, and a bunch of qubits that are used to, one out of two qubits in the lattice that I showed is used to compute, and one out of two is used to extract information about the errors. And you get a bunch of zeros and ones, and you need to say like, haha, there was an X error on that qubit. That's decoding. That's very tough. That's extremely difficult. And in particular because it needs to happen really fast. Because if decoding is slow, there's no point in doing error correction in the first place because this has to be fast, otherwise errors will accumulate. So I'm not an expert in decoding, all of that to say that. And the only thing I can say is that it's a major challenge. I have one of my colleagues, David Poulain, who showed in fact that decoding may require a small quantum computer. So that's also a scary thought. But there's a lot of improvements now with machine learning that lead to decoders that are reasonably fast. I'll stop here because the only thing I can say is it's a real challenge, and improvements have to be made there. Yeah.
We have, because it's already past 1 o'clock.
Yes, thank you for your patience.
So I think we should thank Alexandre Blais again. Thank you. Thanks a lot.